All right, we've been talking about dynamics, which is the explanation of motion, why it's changing, what's going on, and bottom line, it turns into forces. So we talked about Newton's first law of motion, the fact that mass is the determining factor in the inertia of an object and how difficult it is to change its motion. And then we looked at a quantitative aspect of that, which is Newton's second law, F equals ma, which is kind of the basis for a lot of the different things that we're looking at. So we talked about doing free body diagrams and how to visualize forces with vectors and to get a net force by adding up all the vectors of force that are acting on an object to get a predictive result or to explain what's going on using the force ideas and the vectors of free body diagrams. So today I want to talk about Newton's third law of motion, which is, again, you guys have covered in the past, but now I want to look at it with a new perspective. So Newton's third law of motion is that every force exists as a part of a pair of forces. You can't have one force without a equal and opposite pair of that force. And that is what we call an action and a reaction pair of forces. So in other words, I can't push on something without it pushing back at me. If I'm on a chair with rollers and I push on a wall, that wall is going to push on me and I'm going to end up moving away from the wall. Now, the reason is not because the wall is actively pushing, it's because I'm pushing on the wall with more force than the rollers of the chair are pushing on the floor. So the forces on me and the chair are out of balance. The force between me and the wall is equal and opposite. The force between the wheels and the ground are equal and opposite, but the force between the wall and me and the ground are not equal and opposite. So that causes me to accelerate away from the wall across the ground. So when we're talking about the third law of motion, we're not necessarily talking about the forces that we're using in a free body diagram. We're talking about the force that one thing acts on another and the other acts on the first thing. It's more common to say the term for every action is an equal and opposite reaction. For every force is an equal and opposite force. And you can't have one force without the other. I cannot put a force on something without it putting the exact same force on me. I cannot punch a piece of paper without that piece of paper putting force on me, and I can't put more force on the paper than the paper puts on me. So it's a limiting factor in that sense. So everything, when we measure a force, we're going to be measuring a force that acts in both directions. Now, what we're talking about with motion is only the forces acting on an object. So a free body diagram only looks at the forces that are acting on that body, not what that body is doing in return. So that's why Newton's third law sometimes confuses people when they're looking at Newton's second law. All right. So here's some action-reaction pairs. And technically speaking, when a car is rolling down the road, the car is putting force on the road, but the road is putting force on the car. So the road is actually propelling the car forward because that is a force that's acting on the car. The car's force is acting on the road. So the car, we could say the car is pushing the road backward, but obviously in the grand scheme of things, we think of the road as more stationary. Now, in truth, they're moving relative to each other either way, so we could have a different perspective. But when you say the road is actually pushing the car along, that's actually what's happening because the car is moving. The reason the car accelerates is because the forces acting on the car itself are less than the force of the road acting on the car. So the friction between the car and its surroundings is less than the road and the car. So the road's going to propel the car forward and accelerate it. Once it's at the cruising speed, then the force of the road on the car and the force of the air on the car are equal and opposite. So we get no net force, so the car acts at a constant rate. All right. Just like the guy with the refrigerator, he's pushing on the fridge is pushing back at him with a negative amount of his force. The reason the fridge moves is not because he puts more force on the fridge than the fridge puts on him. It's because he puts more force on the floor than the fridge puts on the floor. So if we do a free body diagram on the fridge, we're going to have 4 vectors, one vector of his applied force to the right, one vector down because of the weight of the fridge, one vector up because of the floor, and one vector to the left because of the friction of the floor on the fridge. So we're only looking at his force on the fridge if we're doing a free body diagram of the fridge. We're not looking at what the fridge is doing to him. The space shuttle orbiting the Earth is pulling down on the space shuttle is pulling up on the Earth. And likewise, this low friction demonstration device it's being pushed on, it's pushing back on the hand that's pushing it. So these are all action-reaction pairs that we have to take into account and recognize that forces act in pairs. The other thing that we have to remember is that forces occur in 2 dimensions. We can use that just like we do with velocity and add the forces that are acting on an object. So if we look at this satellite that these 2 astronauts are placing, one is pushing fully to the right and one is pushing with more force up and to the right at a 52-degree angle. So our free body diagram shows the forces acting on those. Well, we're going to take those forces and the components of those forces and add them together to get the total force, which is just taking these vectors, instead of having them tail to tail like they are in the middle diagram, we're going to put them head to tail and end up with like that parallelogram that we see with the total force. And the total force is a sum of the 2 forces that are acting on it. So we can break up a force into its components and use those components and add to what's going on. All right. So then what we have here is the ability to add forces in 2 dimensions, just like we did with velocities, and to have a horizontal and vertical, and to set a coordinate system that works well for that. One of the forces that we use most often is the force of weight. And the thing to keep in mind is that weight is not the same as mass. Mass is the amount of material that something is made out of. Weight is actually a force. It's a force aimed directly downward towards the center of the planet. It's the force of attraction between the planet caused by gravity. And so it has a direction, it has an amount. That amount is calculated by taking F equals ma. In this case, the a is the acceleration of gravity, g. So we see the formula here, W equals mg. That's the same as F equals ma. W is F, the force. Sometimes you'll see me label it as F sub g, or force due to gravity, equals mass times acceleration of gravity. So if you have a mass of 100 kilograms, for example, you're going to weigh 980 newtons. And that's what we have to keep in mind, that weight and mass are different. Weight depends on mass, but it also depends on gravitational pull. So on the moon, for example, 100 Newton or 100 kilogram person is only going to weigh 160 newtons, about 1/6 that on Earth. So 180 pound person is going to weigh 30 pounds on the moon because of the different gravitational pull. So our weight varies based on where we are in the universe. It's still measured in newtons. It's still a force. We don't use negative 9.81 because weight implies that we know the direction is downward and we don't have to worry about that. So we just use 9.81 as the acceleration of gravity. Your apparent weight, what you feel, is going to be different based on accelerating upward or downward. If you're in an elevator, going up in the elevator, when the elevator starts, you're going to feel not just your own weight due to gravity, but also the acceleration of the elevator upward. So it's going to put more force on you upward to accelerate you up. So your legs are going to feel like you're heavier than what you actually are because of the acceleration. Remember, acceleration is what our body feels. We don't feel speed. We don't feel direction. We feel acceleration. So if we're being accelerated upward, we're going to feel heavier. When that high-speed elevator reaches the floor that it's about to stop at and slows down, you feel like there's weight lifted off of your legs because the floor is not supporting your weight as much, and your inertia keeps you going up So it feels lighter as you're slowing down. So we look at our free body diagram, the apparent weight, WA, is bigger than the actual weight because there's an acceleration in the opposite direction of the force of gravity. Another thing that we talk about a lot is normal forces. The word normal, one of the definitions of the word normal is perpendicular. So a normal force is a force that is perpendicular to a surface. That normal force, if we have something sitting on a counter like this soup can, the normal force is equal and opposite the weight. So anytime we have something that is not accelerating up or down, whether it is whatever surface it's on, it's got a normal force and it's perpendicular to the surface. So if we look at this suitcase, the suitcase's normal force, a normal force acting on the suitcase from the floor, is less than the weight of the suitcase because some of the force from the handle is not just to the right, but also upward. So the component of force upward from the handle subtracts some from the weight of the suitcase, so the floor doesn't have to support it with as much force. This is how a sled works, for example. When you're pulling on a sled at an angle, you're also helping lift it out of the snow, so it moves easier as well. Now, more of your force would be moving the suitcase or the sled if it were parallel to the direction that you want to move, but less of it would be pulling it up, so it would still need more force from the floor or from the snow to hold it up, all right? So the normal force from this table with these two idiots pushing the ice block is greater than the weight of the ice block because they both have a component of force that is vertical from their push downward, either 60 degrees or 30 degrees. And so they are adding to the amount of force that the table has to hold up. And so the normal force is the sum of the vertical components of force. The guy on the left pushing down with 60 degrees is pushing with a lot of force downward. The guy on the right is pushing with less force downward, but combined with those and the weight, the normal force has to withstand that. If it can't, the table will collapse and it'll accelerate down. I'm assuming this ice block is held stationary, so that means that these two guys are pushing against each other, so their horizontal components of force are equal and opposite. So we have a net force of 0 on this block, so it just sits there without any acceleration. The normal force on something here describes what would happen and helps us understand how it would go down a hill. So if you look at this snowboarder, if I take this and diagram this out, let's say here's the hill, I know that gravity is acting straight down. So I'm going to put that as my force due to gravity, or the weight. I like to put Fg. The book oftentimes puts W. But the normal force is perpendicular to the hill. So like that. All right. Well, the sum of those two forces, if I move this red arrow, so it is with the black arrow, and it should actually be a little bit longer. The red arrow should. Let me extend that red arrow a little bit more. We see that the result is a net force down. This explains and describes why something is going to accelerate downhill, because the overall sum of the forces acting on it is down the hill. So we anticipate things that are going downhill to accelerate and always end up going faster and faster down the hill. All right, so that's what I wanted to talk about today. We're going to look at how we apply these ideas next week. We're going to do some labs later this week to look at them too. All right, have a great day. Thanks.